Welcome to section 5, optimal model selection. This is lecture 17, threshold optimization using performance metrics. So if we recreate the optimal XGBoost classifier again, and once we've got that trained model stored, we have access to the predict probability method that allows us to make predictions and to return the class probabilities for either the non-fraudulent class or the fraudulent class. Then what we can do is we can explicitly slice the probabilities for the fraudulent class only, and use those as our predictions, which would obviously be the predictions for the probability of being fraudulent, essentially. All right. Then if we want to understand which thresholds we should set our model to, we can do that, I guess, in a number of ways. One of those ways is to optimize our threshold according to some metric. And those metrics would be one or multiple of the performance metrics that we've covered in some of the previous lectures. So for example, area under the precision recall curve, area under the ROC curve, and so on. So in this example, I've chosen the area under the precision recall curve, and I can calculate that by using the sklearn.metrics method. And what I'm going to do is I'm going to initialize two lists. So first a threshold list, which is going to be a list that contains all of the different thresholds that I simulate. Then I'm going to have an area under the precision recall curve list, which is going to store all of the calculated area under the precision recall curve scores that I generate. Then, because this is an experiment, I'm going to use NumPy to simulate a number of thresholds, which are effectively going to maintain a linear space. So it'll be a set of numbers ranging from 0 to 1, and there will be 100 increments of them. So there'll be 100 bins of equally spaced data points within this range of numbers ranging from 0 to 1. So those will be all of our theoretical thresholds. So you could think of the initial threshold there might be a threshold of 0, which would be 0%, and that could range up to 50%, which is typically your classification threshold defaults, all the way up to 100%. And at that threshold, or at that point of the threshold, that's where your classification decision boundary is placed, where if the score that you generate is above that threshold, then you would classify that transaction as fraudulent. And if it's below the threshold, then you would classify it as non-fraudulent. All right, so once we've got these 100 thresholds simulated, we can use a for loop to iterate through each of the thresholds. And then we can update our prediction thresholds value, so the actual classification based on the individual predictions that the model has made in relation to the threshold that we've set. So we've got a threshold, we've got a very low one as a start, and then we can use list comprehension to update all of the thresholds, like I've said, with this condition. So if it's greater than the threshold, then we would classify that transaction as a 1. Otherwise, if it's below the threshold, then we would classify it as a 0. And that's for every element within the ground truth set, so what YPRED, or rather what the model predicted. Then we can actually take these and append the thresholds themselves to a list, which we can use later for plotting and visualization, etc. Then we are going to move on and start to calculate the area under the precision recall curve score. So what we can do there is then take those thresholds, so there's updated classifications based on the threshold, as well as the ground truth, and we can calculate the average precision score for that scenario of where the threshold is. Once we've generated that score, we can then append it to our list of AUPRC scores. And then once that for loop ends, so after the 100 iterations, we'll exit the for loop, and then we can combine the results. So the two lists we can combine into a data frame. We can name them, and then we can go ahead and plot them, add labels, etc. And that gives us this plot below. So here we can see all of the different thresholds that we've simulated. It doesn't make sense to have a threshold below 0 or above 1 or 100%. And then we can see the score of the model at different thresholds. And if you look at it, you'll see that the thresholds start very low, and the classification score according to the AUPRC gets higher and higher, and it reaches a maximum what seems like close to 100% in the 80 range, and then definitely around the 50% mark, which is often your classification default threshold. But based on visual inspection, we won't be able to tell exactly where the highest AUPRC score is. So what we can then do is take our data frame and sort the values by the AUPRC score column, and we can set ascending equals false, which sorts it in descending order. So we can see, well, these are the highest scores and these are the thresholds at those highest scores. And interestingly, the highest scores are actually achieved around the 50% mark. So this model is quite well calibrated already, which is good news, but that isn't always the case. Often with highly imbalanced models, especially if you're looking at anomaly detection models, things like autoencoders and isolation forests and other algorithms like that, sometimes you'd need to take a manual approach to thresholding your model. Then we can also isolate the specific scores that are above a certain range if we want to double check where they lie on the thresholds paradigm. And we can see typically they range from around the 45% mark to around the low 50s.